Thank you, everyone, for coming back to the afternoon session. So we're going to start with Tengren Zhang from the National University of Singapore, who's going to do his first talk, which is on cusped anisotropy representations and cusped Hitchin representations.
Okay, thank you. So before I start, I would like to thank the organizers of this conference, Suyong, Heson, and Zhang1 for inviting me to speak here. It's a pleasure to be here. So if you look at my title and abstract that I submitted, my title was Entropy Rigidity for Cusped Hitchin Representations, okay? And don't worry, I will still get to there. But my original plan before coming to this conference was to kind of give you the proof of that theorem. But I decided that maybe more in line with what we've been doing here, I'm going to spend more time kind of describing the basic theory of this cusped anisotropy and cusped Hitchin representations, which I think will be more useful to most people here anyway. Okay, so I agree with Darryl that a lecture without questions is a failure. So feel free to stop me at any time, okay, to ask questions if you have any. Okay, so let's start. I'm going to start with some basic linear algebra first, okay? So I'm going to let D be integer larger than at least 2, okay? And then my delta is going to denote the set of integers from 1 to D minus 1. And theta is going to be a non-empty subset in delta, all right? Okay, then I'm going to look at this object called the theta flag manifold. So this is a kind of a generalized, maybe, I guess we saw flag manifolds in Francis' talk. And this is like that was a special case of one of these flag manifolds that I'm going to consider. Okay, these are called theta flag manifolds. Okay, so what is an object in this flag manifold? It is a tuple of subspaces, which I denote by Fi1 to Fim, right, which are nested. Okay, and Fij has dimension ij. So it's in the ij's Grassmannian in Rd. And this I1 to In, the dimensions of these subspaces I'm considering, are the elements in theta listed in increasing order. Okay, so in the case when theta equals to delta, then the flag manifold F delta is exactly the flag manifold that Francis was talking about. Okay, but here I'm allowing myself to miss some of the subspaces. Okay. Okay, and then for any element G in SLDR, in the special linear group, okay, I'm going to let sigma 1G to sigma DG denote the singular values of G, okay? So you guys know what singular values are? Yes, okay. Okay, so here's a linear algebra fact, right? That if you take any element G in SLDR, okay, and if it has the property that the Jth singular value is strictly larger than the Jth plus 1 singular value, okay, then there is a unique J-dimensional subspace of Rd, which I denote by Sg to the J, with the property that if you take any vector in that subspace and you apply G to it, its length is stretched by at least the J singular value of G. Okay, so the uniqueness is where you need the strict inequality. All right. Okay. One thing I should mention is that here, when I talk about singular values, you need to choose an inner product on Rd to say what is a single value, and the inner product I choose the standard inner product. Okay. So you can talk about lengths of vectors that are not multiples of each other. Okay. So what's an implication of this? An implication is that if you take an element G in SLDR with the property that the J single value of G is strictly larger than the J plus 1 singular value of G for every J in theta, okay, then you can associate to this element G a particular flag in F theta. Okay, and what is this flag? So this flag I'm going to denote it by U theta G, right? And this flag, the J-dimensional subspace of this flag, is going to be the SGJ that I described above, and you apply G to it. Okay, so you should think of SGJ as the subspace that's maximally stretched, right, by your group element. And the G of SGJ, you take that maximally stretched subspace and you apply G to it. And that's going to be the J-dimensional subspace of my theta flag. Okay, that's my U theta GJ. Any questions about this? Okay. Okay, so another important concept I need, for any non-empty subset theta and delta, I say that this theta is symmetric if a number k is in theta, if and only if d minus k is in theta. Okay? Okay, and then in the case when my theta is symmetric, now I can talk about when two flags in f theta are transverse to each other. Okay, I say that a pair of flags f1 and f2 in f theta are transverse if the k dimensional piece of f1 and the d minus k dimensional piece of f2 stands rd. Okay? Right, so whenever f1k makes sense, f2 d minus k also makes sense because my theta is symmetric. Okay, and since this notion of transality is going to be important for what I'm going to say for the rest of today, I'm always going to assume whenever I say theta now, you should always think of this as me as saying a non-empty symmetric subset of delta. Okay? Questions? All right. Okay, so the first notion I want to introduce are these things called transverse representations. Okay, so I'm going to let gamma be a function group. Okay, so what's a function group? It's an infinite discrete subgroup of PSL2R. All right. Okay, then whenever you have such a group, you can look at its limit set. Okay, so the limit set I always denote by lambda of gamma. And what is this? Well, these are okay. So what you do is you pick a base point O in H2, right? And you look at the gamma orbit of this point. So you apply gamma to this point, you get infinitely many points in H2. And you look at all the possible limits you can get inside of the boundary of H2. Okay, so that's what this limit set is, lambda gamma. All right. Okay, so here's my definition. So my gamma is a function group. I say that a representation rho from gamma to SLDR is theta transverse if there is a continuous rho equivalent map C from the gamma limits, the limit set of gamma to f theta that satisfies two properties that I'm going to explain next. Okay, but let's look at this first. So first, what does rho equivalent mean? So on lambda gamma, I didn't say that before, but the limit set of gamma admits a natural gamma action, right? So whenever you have a PSL2R acting on H2, right, it extends continuously to the boundary of H2, okay? And so your gamma has a natural action on the boundary of H2 as well. And this lambda gamma is a gamma invariant subset. It's in fact a closed minimal gamma invariant subset. Okay. Okay, so it makes sense for this map to be rho equivalent, right? Meaning that the gamma action, this map C intertwines the gamma action on its limit set and the rho gamma action on the flag manifold. Okay, so my rho gamma lives inside of SLDR, and your SLDR acts on the flag manifold, right? Because it takes subspaces to subspaces, so it takes flags to flags. Okay. Okay, and what does continuous mean? So again, lambda gamma here is a subset of the boundary of H2, which is topologically a circle. So I can put the subspace topology on lambda gamma, and then so it makes sense to say whether this map is continuous. Okay, so I need a continuous rho equivalent map C with the following two properties. Okay, so the first property is transversality. So what this says is that if I take two distinct points in the limit set of gamma, okay, my map C will send it to two different flags, okay, and I require those two flags to be transverse. Okay, that's what the transversality is saying. Okay, and maybe the more interesting or less trivial property is this thing we call strongly dynamics preserving. Okay, so what does it say? So here I'm going to draw a picture. There are a lot of words, so I'll draw a picture here. Okay, so what it says is that if you start with any pair of points x, y in the limit set of gamma. So in the picture there, I drew an x and so you should look at the left picture, right? So I have x and y in the boundary of gamma. You should think of those 2 points as inside of the limit set of my function group. So in this picture, again, I draw my x and y to be distinct, but they don't have to be. Okay. So I have x and y in gamma in the limit set of gamma, and I also have a sequence gamma I in gamma with the property that gamma I translates the base point O to x, and the gamma I inverses translates the base point O into y, right? So that's what I drew here, right? So my O here and my base point, I'm thinking of it as the origin in the disk, and when I apply my gamma 1 O, gamma 2 O, and so on, it goes to x. But if I apply gamma 1 inverse O, gamma 2 inverse O, and so on, it goes to y. Okay? So this is my starting setup. I assume I have my pair of points x, y, and my sequence gamma I with this property. Okay? then this map C, for it to be strongly dynamics preserving, means that when you look at rho of gamma I, okay, and you apply to any flag f in f theta that's transverse to cy, it has to converge to cx. Okay, so on the right hand side, you should think of this as a picture in f theta. Okay, and then in my f theta, I drew my flags cy and cx, and this green curve through cy is supposed to describe all the flags that are not transverse to cy. Okay, so that's a small subset. Okay, its complement is dense and open in the flag manifold. And if you take any f that is not on the green curve, so not that is transverse to cy, and you apply the rho gamma i's to it, it needs to converge to cx. Okay, so what is this? How do I think about this definition, right? So if you look at this, if you start off with a sequence gamma I with this property on H2, right? A consequence of this is that if you pick any point in the boundary of H2 that is not equal to y, and you apply gamma I to it, it has to converge to x. So if you look at the boundary of H2, this is saying that, okay, aside from y, if you take the complement of y, everything gets sucked into x if you apply gamma I to it, okay? And you want your map C to transfer this property into the flag manifold. Okay, so now in my flag manifold, okay, I cannot just say not equal to cy, but as long as you're transverse to cy, everything must get sucked into cx when you apply this sequence of group elements. Okay, so this is what I call strongly dynamics preserving. Any questions? Okay, so this is the definition. Okay, I haven't given you any examples of this, so okay, but let me just but in order for me to talk about the examples, let me just describe some basic properties of this strongly dynamics of this theta transverse representations. Okay. Oh, okay. One more piece of notation. The map above C, the strongly dynamics preserving property here ensures that if such a map C exists, then it has to be unique. Okay, so because of that, I refer to this C as the theta limit map of rho. Okay, yeah. No, but in fact it is. It is uniform, right? So yeah. So in fact, if you look at if you take any um, compact subset of f theta that doesn't intersect this green curve, right? And you look at then on that compact set, it will converge uniformly to Cx. Okay. Very good question. So if you look at, so what this ensures, right, is that if you look at the image of the limit of this, okay, so you have your limit set, you look at the image under C. So there you have, the image is going to be invariant under rho gamma, okay? And the rho gamma action there is a convergence group action. So in some sense, right, this C here, what we're doing is we are saying the convergence group action on the boundary of on the limit set of gamma has to be transferred into the flag manifold. Okay. Yeah. Any other questions? Okay. So some properties of transverse representations. Okay, so all of these properties pretty much follow from this linear algebra proposition. Okay, so let me go through it carefully. So what this linear algebra proposition says that if you have two flags, f plus, f minus in f theta, okay, they don't need to be transverse, they can be equal, okay? And you have a sequence gi of linear maps in SLDR, then the following are equivalent. Okay, so the first statement is that if you look at this u theta gi's, okay, okay, so here I'm okay, so the u, okay, maybe yeah. So yeah, here I gave the wrong definition. Okay, so there's a definition of u theta gi's that does not require a single. So the way that I define u theta gi's, I assume that your gi had a singular value gap for all the j's in theta, right? Okay, but in fact, if you don't have single value gaps, you can also define this u theta gi's. It's just that it's not unique. Okay, so maybe let me clarify that. Let me go back a bit to clarify that. How do I go back? Oops. Yeah. Okay. Oh, okay, so I go back. Okay. Okay, so here when I define this, so okay, so if you look at this statement here, right? If you don't have a singular value gap, you still have a j-dimensional subspace SGJ with this property. Okay, the problem is if you don't have strict inequality here, that subspace is not unique. Okay, but you still can have these SGJs, and then you can use that to still define this U theta G. Okay, but now it's not unique anymore. Okay, but for okay, if you have the gaps are strict, then it's unique. Okay, but if you're not unique, okay, that's still okay. So here, when I say this U theta GI, I just pick some U theta GI for each GI. Okay, and suppose that converges to F plus, and the U theta GI inverses converge to F minus, and oh, I guess okay, maybe I didn't have to do that. And the gap of sigma sigma JGI over sigma J plus 1 GI has to go to infinity, right? So this is the first set of conditions I'm imposing on my sequence. Okay, this is equivalent to the following. Okay, so the second set of conditions is saying that if you take any f in F theta that's transverse to F minus, and you apply your GIs to it, it converges to F plus, and this convergence is uniform on compact subsets of flex that are transverse to F minus. Okay. Okay, so these two are equivalent, and the last one is you can find open sets U plus and U minus in F theta, so that GIF converges to F plus for all F in U plus, and I inverse F converges to F minus for all F in U minus. Okay, so this is a linear algebra fact. Yes. So actually in this, I realized after I read it again that it doesn't matter because my assumption here, right, ensures that as if you go far along the sequence, you will have a gap, right? Because I'm requiring here that I'm requiring that the ratio of sigma JGI over sigma J plus 1 GI needs to go to infinity. So in particular for large enough I, they must be distinct. Okay, so maybe initially along your sequence, they might not be unique, but once you go far along the sequence, it's going to be unique. Okay. Okay, so this is like the key kind of linear algebra proposition that sort of everything runs, kind of that everything uses here. Okay, the point here is that whether or not your singular values go to infinity, right, can be geometrically, if you want your ratio of singular values to go to infinity, what does it mean? It means that you can find open sets that get sucked into your F plus and F minus. Okay. Okay, so that's that. Okay, so before I state the properties that I want to deduce from this proposition, I need some terminology. So I say that an element G in SLDR is theta proximal if the kth eigenvalue of G is strictly larger than the k plus 1 eigenvalue of G. Okay, so I guess I did not write down what the lambda kg is, but basically every time you have a G, I'm gonna let lambda 1G to lambda dg denote the absolute value of the generalized eigenvalues of G. Okay, so I'm not assuming that G is diagonalizable or anything like that, right? It's just the absolute value of the generalized eigenvalues. So the eigenvalues can be complex. Okay, I just take that. I just want to see how big they are. Okay, and then and then for any G in SLDR, you can decompose this G into a semi-simple part and a unipotent part. This is called the Jordan-Chevalier decomposition of G. So what does the semi-simple part look like, right? So basically what you're doing is, really what you're doing is you're taking G and you're writing it in this Jordan normal form. Okay, so your G semi-simple is a block diagonal matrix where the blocks are either size 1 or size 2. The size 1 blocks correspond to the real eigenvalues of G, and the size 2 blocks correspond to the complex the complex eigenvalues of G that are conjugate to each other, right? Each 2 by 2 block. And then this GU is a unipotent matrix that commutes with this GSS, the semi-simple part. Okay? So you can always decompose every G like this. And then I say that G is weakly unipotent if the absolute value of all the eigenvalues of G are 1. So I'm not assuming they are real. I just need the absolute value to be 1. Okay. And the unipotent part, right, is not the identity. Okay, so this is what I call weakly unipotent. Okay. Okay. All right. So here's a corollary of the proposition, what you can say about these data transverse groups. Okay, so the first thing you can say is that if you take any infinite sequence gamma I and gamma, so I start with a data transverse representation rho. If I take any gamma I and gamma, and I look at the logarithm of the ratio of single values of rho gamma I, that has to go to infinity. Okay, and that's because I'm using the fact that condition 3 implies condition 1. Okay, you can deduce this singular value gaps going to infinity from looking at the dynamics of u plus and u minus on my flag manifold. Okay. Okay, and the second thing also, okay, but this one is you're looking at again using 3 implies 1, but you're looking at the first 2 parts instead of the third part, right? So what you can deduce is that the image of this map C, right, inside of the flag manifold is really just the set of limit points of the u theta of rho gammas whenever u theta rho gamma is well defined. Okay, so here notice that as a consequence of condition 1, u theta of rho gamma is unique for all but finitely many of the gammas, right? Because my singular value gaps are all going to infinity. And so, okay, aside from finitely many elements in a group, my u theta gamma is well defined. So this is an infinite set. I'm looking at the set of limit points of this. Okay, that's what this what CL of lambda gamma looks like. Okay, that's again a consequence of this proposition. Okay, and then third and fourth, oops. Okay, so it tells you where parabolic and hyperbolic elements in gamma get sent to. What kind of elements the new get sent to? Okay, so if gamma in gamma is parabolic, okay, meaning that it's conjugate in SL2R to 1101, okay, then its image under rho has to be weakly unipotent. Okay. And so basically the reason for that is okay, and then if it's hyperbolic, then your rho gamma has to be proximal, theta proximal, as described above. So parabolic, okay, gamma and gamma, so my gamma is a function group. So little gamma and big gamma being parabolic means that it is conjugate to 1101. Yes. Yes. So instead of gamma, being parabolic is saying that the group element corresponds to one of the cusps. Yes. Okay. And then being hyperbolic means that it's conjugate to something on the form lambda 001 over lambda, where lambda is bigger than 1. Okay, inside of my function group. Okay, and how basically where do these two facts come from, right? Basically, if you look at your little gamma in big gamma, right? If it's parabolic, it's going to have a unique fixed point in lambda gamma. Okay, so if you apply this proposition here to the sequence of rho, the GIs that are going to apply are just the powers of rho gamma n. In that case, your F plus and F minus will be the same point. Okay, in the case when it's hyperbolic, then the F plus and F minus are distinct points, and when they are distinct, they have to be transverse. Okay, so that's how that. Okay, so that basically follows from that kind of observation. Okay, so these are kind of maybe the first properties of these data transverse representations that we can get. Any questions about this? Yes. Sorry? Right. So now I don't. So okay. So what the definition is? I didn't write down what the lambda IG is. Okay, but basically every time you have a G, you write it in you view it as a complex element in SLDC, and you write it in the Jordan normal form, right? And you look at the diagonal values, the diagonal entries of that guy. Those are complex numbers. Maybe some real, some complex. Just take the absolute value of all of them, and then you list it in weakly decreasing order. So lambda 1G is the biggest, lambda DG is the smallest. Okay, so that's what the lambda IG is here. So when I say k theta, let's say k proximal, it means that I have my lambda kg has to be strictly larger than lambda k plus 1g, but for the rest, they can be equal. I don't care. Okay. And then of course, if you want like Benoit's proximality is lambda, you want it to be 1 proximal. So you have a distinguished top eigenvalue, and then the rest of them has to be strictly smaller, in which case your top eigenvalue has to be real, right? Because they all come in complex conjugate pairs. Any other questions? Okay, so so these are my transverse representations. So my main example that I want to apply this technology to, right, is these things that I call continuously positive representation. So this is a name that I just made up for this talk. So I'll explain to you why. Okay, so what are these continuously positive representations? So first, I need a notion of what is a positive map. Okay, so I start with a subset S of S1. So this S can be infinite, can be all of S1, can be finite, I don't care. Okay, the only condition is that it has to be at least 3. Okay, then I say a map C from this S to this flag manifold, the complete flag manifold now. Okay, my theta equals to delta is positive if for all points P1 to Pn listed in this cyclic order along S, they must, if you look at C of P1 to C of Pn, this has to be positive. Okay, so along S1, you have a natural cyclic order. Okay, and and I say a tuple is positive if it's ordered along the circle in this cyclic order, and a map C from S to F delta RD, that F delta RD is positive if it takes positive tuples inside of my circle to positive tuples of flags. Okay, and the positive tuples of flags are exactly what we've been looking at Francis' mini course so far. Okay. Yeah, any questions about this? So here is full flags, F delta. This only makes sense for full flags. Okay. Any other questions? Okay. Okay, then now I'm going to take any function group. So this can be infinitely generated, whatever, I don't care, just a discrete infinite subgroup. Okay. I say that a representation rho from gamma to SLDR is continuously positive. Okay, if there is a continuous positive rho equivariant map C from the limit set of gamma into the flag manifold F delta RD. I'm missing a D there. Okay. Okay, so right. So this lambda gamma is a subset of the boundary of H2, which is a circle. So there's a natural cyclic order on the lambda gamma, right? So positivity here makes sense. All right. So these are positive maps. Okay, and then in the case when gamma is a geometrically finite group, okay, that means that, well, okay, since I'm inside of PSL2, this is the same thing as saying that it's finitely generated and non-elementary. Okay, then continuously positive representations, I call them cusped Hitchin representations. Okay, so like I said, this continuously positive representation terminology, I only made it up for this talk because in our paper, we focus mainly on the geometrically finite case. So we only talk about cusped Hitchin representations. Okay, but some of the stuff that we do, you don't need finite generation for it. Okay, so in this I guess talk, I'm just trying to separate the two, trying to specify exactly when I need finite generation and when I do not. Okay. Yes. No. So my S, yeah, for every possible finite subset, it has to be sent to a positive tuple. Okay. Yeah. Any other questions? Okay, so so here I'm justifying some terminology. Okay, so if gamma in PSL2 is a closed surface group, right? Then a representation rho from gamma to SLDR is called a Hitchin representation. If it lies in a connected component of the space of homomorphisms from gamma to SLDR that contains a representation of the form tau D composed with J, where J from gamma to SL2R is a discrete and faithful representation. And tau D from SL2R to SLDR, which I'm thinking of as SL of the D-1 symmetric tensor of R2. Okay, so I think in Francis' talk, we saw a lot of the wedge, but here I'm taking the symmetric tensor. Okay, so this guy here is the representation of the induced action of SL2R on the D-1 symmetric tensor. So the base, let's say you take a basis E1 and E2 for R2, a basis for the D-1 symmetric tensor is like E to the 1I, E sub 1I, E sub 2 to the D minus I, where I goes from 0, D. Okay, so that's D-1 different basis vectors. And you have a natural SL2R action on that, right? Where you just act on every piece of your basis vector. Okay, and that's a linear action, so that gives you a representation from SL2R to SLDR. Okay, sometimes people, this is just, okay, up to conjugation, this is the unique irreducible D-dimensional representation of SL2R. Okay, so, but that's maybe a more explicit description. Okay, so these are called Hitchin representations. Okay, and it's in the paper of Ford-Gontroff that Francis has been complaining about. They actually proved this theorem. Okay, but again, it's kind of one of those things where it's really hard to abstract the proof from that paper. Right? So what they show is that if you, in the case when you have a closed surface group, okay, then your lambda gamma in this case is the entire boundary of H2. So that's a full circle. Okay, and they show that a representation from gamma to SLDR is Hitchin if and only if there is a positive row equivariant map from the limit set of gamma into the flag manifold, not SLDR, into the F delta RD. Okay, into F delta RD. And also if C exists, then it's necessarily continuous. Okay. So okay, I see a few people making faces. The continuity is not super. Okay, so the point is when you look at positivity, right? There's a certain okay, maybe I don't know how much I should explain this. Okay, maybe let me not maybe I can talk a little bit more about it next time. Okay, so this is continuous. Okay. So this is what they proved. And so from this result, right, you can see that where my terminology is coming from. Okay, because in the case when my gamma is a closed surface group, then my cusp Hitchin representation that I defined above are exactly just Hitchin representations. Okay. Okay, so the next thing I'm going to say about, I just added it in after lunch, after some conversation with Francis. Okay, so I want to compare them with these things called positive representations that I think Francis is going to talk about tomorrow. So I hope I'm not stealing your thunder too much. So here, I'm going to take gamma in PSL2R to be a non-uniform lattice. So you can think of as a finite, an example of this is a finite area surface. Okay, a non-uniform lattice with cusp, finite area surface with cusp. Okay. And then I'm going to look at this subset lambda p gamma instead of lambda gamma, which is a set of fixed points of parabolic elements in gamma. So this is a countable dense subset, right, inside of boundary of H2. Okay, then a representation rho from gamma to SLDR is a positive representation if there is a positive row equivariant map C from this fixed points of parabolic elements into F delta RD. So again, equivariant here makes sense because these fixed points of these parabolic elements is gamma invariant. Okay, and it's a subset of the circle, so positively makes sense as well. Okay, so this C is usually called the framing of the representation. Okay, and I think Francis is going to talk more about that tomorrow. Okay, but I want to compare these guys with the cusp Hitchin representations that I defined. Okay, so what's the difference? If you look at just the definition, right? First, my cusp Hitchin representations are defined on the entire limit set. But these guys are only, so first thing, my gamma, for cusp Hitchin representations, my gamma just need to be geometrically finite. Okay? But for the positive representations here, I need a non-uniform lattice. Okay, that's one difference. A second difference is that when I define these cusp Hitchin representations, my positive map goes from the entire limit set into the flag manifold. For the positive representation, I'm just going from the fixed points of parabolic elements. Okay. Third difference, here I require a continuity for my limit map C. Okay. For the framing, you don't require any continuity. Okay. All right. Okay, but but they are related. So how are they related? So if gamma is okay, so maybe let me just put a caveat for what I'm going to say next. I don't think it's written down anywhere. Okay, but I think I know how to prove it, and I think it's true. So you shouldn't really just believe me, but if you want, I can tell you the argument later. Okay. So here's what I'm gonna say. Okay, let gamma be a geometrically finite function group, and let gamma prime be a function lattice. Okay, and suppose that there is an isomorphism iota from gamma to gamma prime, such that an element gamma, little gamma and big gamma is peripheral if and only if iota gamma in gamma prime is peripheral. Okay, so what am I doing here? So here's a picture, right? On the left-hand side, I have my geometrically finite function group. Okay, I mean, this H2 quotient out by a geometrically finite function group. On the right side, I have my lattice, H2 quotient out by my lattice. Okay, and this map iota is supposed, so what it does is it sends the two cusps on the left to the two cusps on the left, but it sends the flares on the right to the two cusps on the right. It sends the flares on the left to the two cusps on the left. Okay, so this gives you an isomorphism of the fundamental groups of these two manifolds. Okay, they will not extend to any kind of map on SL2, on PSL2R, but you get that because these two things are homeomorphic, right? So you get a map induced map on the fundamental groups, and that's what my iota is supposed to do. Okay. Okay, and then then the following are equivalent. So this is my claim that you should take with a pinch of salt. Okay, if rho from gamma prime to SLDR is okay, so what am I making equivalent, right? There's on the number one, there's some positivity statement, some statement about positive representation. So these are things that are with positive maps that are only defined on the parabolic fixed points. Okay, and then I want to compare that to things that are cusped Hitchin. Okay, so okay, let's go through the statement. So the first one is I just look at the right hand side, right? So my gamma prime. So I have a lattice. I have a representation rho from gamma prime to SLDR that's positive, with the property that if you look at rho composed iota gamma, okay, this is weakly unipotent for all gamma and gamma, and rho composed iota gamma is delta proximal for all peripheral hyperbolic gamma and gamma. Okay, so what does it mean? This means that you have a positive representation defined from here, with the property that if you look at, so let's say if you look at this cusp, right? If it came from a cusp, then it has to be sent to a weakly unipotent element. And then let's say you look at this cusp here, if it came from a flare, then it has to be sent to a delta proximal element. No, you're right. I want to assume they are homeomorphic. Sorry, yeah. Thank you. Yeah. You're right. Thank you for pointing that out. Yeah, so this is not strong enough. My isomorphism here has to be induced by isomorphism of H2 quotient out by the gammas. Yes. Okay. Okay. Yeah, and so once you have that, then that's equivalent to saying that the representation rho composed iota is cusped Hitchin. Okay. So basically, you can, if you assume that your rho kind of preserves the type of your N, you can extend that to a continuous map. That's my claim. Okay. Okay, but that's not really super important for what we are going to say next. This is just I want to kind of justify why I don't call these cusped Hitchin representations just positive representations, because they are a bit different, right? And but the difference is a little subtle. Okay. Okay, and so the theorem here is that if rho from gamma to SLDR is continuously positive, so here I don't assume my gamma is geometrically finite, okay, then it is delta transverse and irreducible. Okay, so in other words, when you're continuously positive, right, so you have a r-equivariant continuous positive map, okay, the positivity ensures that you have this transality. And what I'm claiming, okay, that's easy to see. Okay, I guess that's what Francis told us as well, okay? But what I'm claiming is that this positivity actually ensures that you have this strongly dynamics preserving property as well, okay? And it's also irreducible, okay? But irreducibility is not super difficult as well. Okay, the kind of the most non-trivial part is to show that it's strongly dynamics preserving. Okay, and the kind of the idea for why this is true is because whenever you have a positive triple of flags, right? this triple of flags actually defines for you an open set in the flag manifold. Namely, okay, maybe I should just write something here. So if you have a positive triple, right? Let's say I draw in SL3, so I have F1, F2. Okay, and then you have a so something like G like this. So this is a positive, what a positive triple of flags look like. Okay, then this triple defines for you an open set in the complete flag manifold. Namely, you look at the flags where the point part lies in this triangle, projective triangle. So this is, so okay, what am I doing? I'm looking at F1 and F2. I'm looking at all the possible spans of subspaces by this F1 and F2. Okay, so you have a two-dimensional part of F1, you have the one-dimensional plus the one-dimensional part here, and the two-dimensional part of F2. Okay, and then so that cuts your space into a bunch of triangles, and one of the triangles is contain the one-dimensional part of G. Okay, so I'm going to look at all I'm going to look at a set of flags where the point part has to lie in this same this triangle, and then the line part has to be and also is positive. That means F1, H, F2 is positive. Okay. So I'm going to look at all the possible H's like this. Okay. So this is the key point, right? Once you have a triple of flags, this defines for you an open set, right? In a very canonical way, right? In the flag manifold. Okay. And then now you can imagine that if you apply a sequence of group elements in gamma, so you pick 2 points in your limit set, right? And you apply your group element gamma, and these 2 points get sucked to the same point in the limit set. Then if you look at the corresponding flags, right, by the positive flag map, these flags must get sucked together as well, okay? But this ensures that you have this open set that gets sucked into a single point, okay? And then now you can use the key linear algebra proposition to deduce that you have this strongly dynamics preserving. You have property, right? You have this open set where everything gets sucked to a point. That tells you that if you're transverse to a repeller, everything gets sucked to a point. That's kind of the idea there, okay? But again, this again follows from that key linear algebra proposition. Okay, and then also you can say that if gamma is parabolic, then either rho gamma or minus rho gamma is unipotent with a single Jordan block. Okay, so you have a minus rho gamma here is because the natural thing to look at is really rho from gamma to PSLDR. Okay, because I'm doing projective geometry. Okay, and so if you lift it to SLDR, then your rho gamma, your rho gamma is either unipotent or minus rho gamma is unipotent as well. Okay, so that's okay, so this minus sign there's nothing very weird going on. It's just when I lift, because here I'm looking at representation SLDR. Okay. Any questions about this? Okay, so this is the key example that I would like to I want to think about when I want to apply these transverse representations to. I should also comment that when I define transverse representations here, I did it for a discrete friction group, right? But you can do this in a much more general setting as well. Okay, so the setting we do it is these things called what we call a projectively visible group. So this is a discrete subgroup of PSLDR that preserves a properly convex domain with the property that along the orbital limit set of this gamma inside of the properly convex domain, you must look like you're strictly convex and C1. Okay, meaning every point in the orbital limit set has to have a unique supporting hyperplane. You take any 2 points in the limit set, the chord between them has to lie in the domain. Okay, but anyway, so that's not that. I'm not going to focus on that today. Okay, but my point is that these transverse representations, you can imagine, can be defined in a much more general setting. Okay, the point is that you need to have some metric space where your O can live, and then you have some limit set on the boundary, okay, which has convergence group actions kind of dynamics, and then you can make this definition. Okay. Okay, so the next thing I want to discuss are these things called cusped and also representations. Okay, and basically the motivating question is for these transverse representations, right? Okay, there are a few things I can say. Okay, like in this corollary, but in the case when gamma is a geometrically finite group, when I have some finiteness, right? What more can I say? Okay, so that's the motivation of the next part. Okay. Okay, so here I'm going to introduce this thing called cusped and also representations. Okay. So here I'm going to assume that my gamma is a geometrically finite function group. Okay, and there are a few things. Okay, so here I need to make a pretty complicated construction. So I'm going to, okay, so, actually I'm running out of time. So, okay, maybe I'll just try to finish this definition. Okay, so I'm going to let U gamma be a subset of the unitangent bundle of H2 consisting of all the vectors V whose forward endpoint V plus and the backward endpoint V minus both lie in the limit set of gamma. Okay, and then you can check that this U gamma, right, is a gamma invariant subset that's invariant under the flow as well. Okay, so let me just see if I have a picture. I don't have a picture. Okay, maybe I have. So what am I doing? Okay, maybe the picture here. So if you look on the left-hand side, right, basically, if you look at U gamma and you quotient out by gamma, what you're looking at is you're looking at the flow lines of the unit tangent bundle of this surface on the left that stays entirely in the complement of the flares. Okay, so you can go deep into the cast and come back out, that's okay, but you cannot go into the flares, the flow lines. Okay, so in other words, this is the recurrent part of the geodesic flow, right? So this is kind of the more interesting part of the geodesic flow. That's what this U gamma is, okay? In the universal cover, all right? And then, okay, and then this U gamma is gamma invariant, so you can quotient out by gamma to get this set U hat gamma, okay? And then the geodesic flow phi t descends to the geodesic flow, a flow on U hat gamma, okay? Okay, then now, so far, this is just about the group. Now I'm going to put in my representation. So I have a representation rho from gamma to SLDR. Then this gamma, this representation allows you to define a gamma action on this product bundle. So what am I doing? So I'm looking at just the product U gamma times RD, and I view this as a rank D real vector bundle over U gamma. Okay? I'm going to call this E rho. So the rho dependence here is because this bundle comes with a gamma action, right? And the gamma action is given by this, right? Gamma times Vx, right? On the base, you just translate it by gamma, and on the fiber, you move it by rho gamma. Okay? So you have this gamma action. Okay, also the flow phi t on U gamma lifts to a flow on E rho. Okay? And what's this flow? Well, phi t of Vx, you just apply phi t to V and just keep X constant. So this is a trivial bundle. Downstairs, when I flow it, upstairs, I'm just keeping it keep the vector constant, just flowing. Okay? Okay, then you can check that this flow actually commutes with the gamma action that I defined. Okay, and so your flow actually descends to a flow on the quotient bundle. Okay, so I take this E rho, I quotient out by gamma. I get this vector bundle, which I call E hat rho over U hat gamma. Okay, and this flow phi t here descends to a flow on E hat rho. Okay, so here's a picture of what we have so far. Okay, so I started off with my U gamma. Okay, oops. I started off with my U gamma, which is covered now. Okay, so this was U gamma. Okay, and then you had gamma, so it's quotient out by gamma. Above this guy, I took the trivial RD bundle, right? And then you have a gamma action here given by a representation. So you can build this quotient bundle E hat rho, which is a bundle over U hat gamma. All of these guys emit the flow, PT. Okay, which basically is the same. I use the same notation for all of them, all four flows. Okay. Any questions about this? Okay, so far I can do this for any representation I want, right? Any representation as LDR. Okay, then now I'm going to throw into the mix the existence of this continuous row equivalent transverse map. Okay, so suppose that I have this continuous row equivalent transverse map C from the limit set of gamma into FKD minus KRD. So this is a flat manifold. We have a K dimensional subspace and a D minus K dimensional subspace. Okay. Then you can, using this map, you can define continuous subbundles of E rho, okay, in the following way. So if you take any vector in the base, okay, this theta K is a rank K subbundle of E rho, okay, and the fiber above the point V is this K dimensional subspace CKV plus. Okay, so you look at the forward endpoint, that's a point in the limit set. Okay, the flag map gives you a K dimensional subspace, you just use that, okay? And then this CD minus KV, what you do is you go backwards. You look at the backward endpoint. Your flag map C gives you a D minus K dimensional space, and you use that. Okay, so this constructs for you two subbundles of E rho, and it's easy to see that they are flow invariant. And the fact that your C is rho equivariant tells you that these subbundles are also gamma invariant. Okay. Furthermore, the transitality tells you that this is a splitting. Right? The transitality of this map tells you that these two bundles above every point, right, the fiber, you look at the sum actually gives you the entire RD. Okay? Okay, and so this is a continuous gamma invariant phi t invariant splitting. And so again, it descends to a continuous phi t invariant splitting on E rho hat, okay, by quotient out by gamma. Okay, so this is the picture you have. So in the center, that's the same picture we had before. So now this E rho, you can split it into this theta k and C d minus k, and that descends to a theta hat k and C hat d minus k on the other side. Okay? Okay, so now we have all these things. We can finally make the definition, and maybe I'll stop here right after the definition. Okay, so gamma is going to be a geometrically finite function group, and k is any number in delta from 1 to d minus 1. Okay. Then I'm going to let this guy here be, I pick a continuous norm on E hat rho, U hat gamma. So what does it mean? This means that I want to pick a norm on every fiber of E hat rho, which is continuously varying as I vary on my base. Okay, I pick any such norm. Then I say a representation rho from gamma to SLDR is cast K and north south with respect to this norm if the following conditions hold. Okay, so first there is a continuous r-equivariant transverse map C from lambda gamma to FKD minus KRD, which induces this splitting. So that's what we've been talking about for the last 5 minutes, right? Okay. And then the second condition is basically saying that the flow on E hat rho has to be a north-south with respect to this splitting. Okay, so more precisely, there is some constant big C greater than or equals to 1 and little c greater than or equals to 0, such that if you pick any positive time, okay, any vector v in the base, and any vector y in the fiber of theta hat k over v, and any vector z in the fiber of c hat d minus k over v, I guess I need y and z to be non-zero. I forgot to write non-zero. Okay, pick non-zero vectors. Then if you look at this y and z, so they live above v, as you flow, right? As you flow them, you measure the lengths of these two vectors with respect to the chosen norm. Okay, you require that the norm, as you flow, the ratio of these two norms must be contracting exponentially. Okay. So this is what a cusp and north-south representation. Okay, cusp and north-south with respect to a certain norm. Okay, then I say that a representation is theta and north-south with respect to the norm if it's cusp k and north-south with respect to the norm for every k in theta. Okay, and also I say that a representation rho is cusp theta and north-south if it is cusp theta and north-south with respect to some continuous norm on E rho hat U hat gamma. Okay. So I'm already 2 minutes over time, so at least I got to the definition, and we can continue next time. So formally the definition is the same. Okay, but the big difference is that in the traditional notion of a cusp of a north-south representation, you require that the flow space is going to be compact. So usually they're working with a Gromov hyperbolic group. Okay, and then there you can construct a flow space which is compact. Okay, so that flow space is going to be compact, and you do the same thing. Now there's a big difference because there any two norms, because of the compactness of the base, any two norms on the fibers are bi-Lipschitz to each other. So if you require this contraction property, it doesn't depend on the norm you pick. Here, a priori, it depends on the norm you pick. Okay, but the punchline of this story is that actually that it doesn't. Okay, there's in a certain sense that I'll try to explain next time.